This video is part of a series where we translate VMware concepts into their KVM equivalents. In this episode, we focus on the core architecture, and in the next ones we'll cover networking, storage, and higher-level platform services. If you're a VMware engineer, KVM often feels confusing, not because it's worse, but because it doesn't look like vSphere. KVM is not a single product. It's an ecosystem. So in this video, I'm not going to re-explain virtualization fundamentals. Instead, I'm going to translate vSphere core concepts, things you already know from ESXi and vCenter, into their KVM core equivalents, Linux, KVM, QEMU, and libvirt. By the end, you won't just know the names. You'll understand where the responsibilities live and why KVM behaves the way it does. One quick clarification before we start. When I say vSphere, I'm not talking about a single product. vSphere is a platform made up of multiple components, including VMware ESXi, vCenter, and cluster-level services. In this video, when it's useful, I'll sometimes compare ESXi directly to KVM because they both occupy the hypervisor layer. When the comparison is broader, I'll refer to vSphere as the full platform. Let's start by killing one of the biggest myths right away. ESXi is correctly called a Type 1 hypervisor. KVM is often incorrectly called Type 2. Here's the reality. Both ESXi and KVM are Type 1 hypervisors. KVM runs in kernel space, directly on bare metal. The fact that Linux is a general-purpose operating system does not make KVM Type 2. In both cases, the hypervisor logic runs directly on hardware. Before we compare features, we need to compare architectures, because this difference explains almost everything else. In the VMware world, ESXi is the operating system. vMkernel replaces Linux. It handles CPU scheduling, memory management, NUMA, networking, storage, and drivers. On top of that, VMware runs VMX-World and host agents, all tightly integrated into a single purpose-built platform. In the KVM world, the philosophy is completely different. Linux is the operating system. The Linux kernel already handles scheduling, memory, NUMA, networking, storage, and drivers, just like it does for any other workload. KVM itself is not a hypervisor in the traditional sense. It's a set of kernel modules, kvm.ko, and a CPU-specific module that add virtualization capabilities to the Linux kernel. Once those modules are loaded, Linux becomes capable of running virtual CPUs and managing guest memory. But that's all KVM does. KVM exposes kernel APIs for CPU and RAM virtualization only. By itself, KVM has no concept of disks, network cards, or devices, and it has no user interface at all. This is where QEMU comes in. QEMU is the user space virtual machine process. It uses the KVM kernel APIs to execute guest code efficiently, and it completes a virtual machine by providing device models, networking, storage, firmware, and platform logic. Together, KVM and QEMU form the execution core of virtualization on Linux. On top of that sits libvirt. Libvirt is a standard management API and daemon. It doesn't execute virtual machines. It defines, configures, and manages them. Tools like Version Virt Manager are simply client of libvirt, just like vCenter talks to ESXi host agents. So architecturally, KVM is not a monolithic product. It's an ecosystem built from standard Linux components, kernel modules, user space processes, and management APIs. And this single design choice explains most of the differences VMware engineers notice when they move to KVM. Every VMware engineer knows VMware tools, but it's important to understand what role it actually plays. At its core, VMware tools gives the guest OS awareness of the hypervisor. It establishes a privileged communication channel that standard hardware emulation simply doesn't provide. This enables fundamental virtualization features like file system quiescing for backups, memory ballooning, clean power operations, and guest state reporting. On top of that core role, VMware Tools also bundles optimized drivers and a set of convenience features like time synchronization, mouse integration, and clipboard sharing. So VMware Tools isn't just about performance. It's about coordination, integration, and manageability. In the KVM world, these same roles exist, but they are deliberately split into standardized components. Guest-host coordination is handled by the QEMU guest agent, which provides shutdown, quiescing, and guest state reporting. High-performance I/O is handled separately through Versio drivers for networking, storage, and memory management. There is no single tools package, not because KVM is missing features, but because these functions are designed to integrate directly with the operating system. This separation is one reason KVM feels very natural with Linux guests. Performance, coordination, and OS services each live where they belong. Before talking about disk provisioning and compare VMware and KVM, let's quickly align on terminology. Thick provisioning means a full disk size is allocated on the data store creation, either eagerly or lazily zeroed. Thin provisioning means space is consumed only as data is written, up to a defined maximum size. Both models exist in VMware and in KVM, but they're enforced very differently. In VMware, the hypervisor enforces provisioning rules at the data store level. The data store abstraction tracks allocation, prevents overcommit surprises, and gives you guardrails. In KVM, provisioning is simply storage behavior. A raw disk is thick. A Cow2 disk is thin. Ceph RBD is thin by default. There is no data store abstraction protecting you here. Overcommitment is real, and it's explicitly your responsibility. vMotion is one of VMware's crown jewels. It integrates CPU compatibility, storage, and memory migration into a single, guarded workflow. Features like EVC allow vSphere to automatically mask CPU differences, so migrations just work across a cluster. KVM also supports live migration, and at a technical level, the mechanism is very similar. The key difference is this: KVM does not provide a built-in equivalent of vSphere EVC. CPU compatibility is not automatically enforced. You must explicitly define which CPU features a VM is allowed to see. This gives you more control, but removes the guardrails. The migration mechanism itself is very similar in VMware and KVM. Memory is copied while the VM continues to run. The real difference is the CPU contract. In VMware, EVC defines a baseline CPU before the VM ever boots, so the VM never sees features that might break migration. In KVM, the default is host pass-through. The VM sees the real CPU. That gives you maximum performance, but it means live migration only works if the destination CPU is compatible or if you explicitly define a CPU model. Same technology, different responsibility model. In VMware, networking introduces a very important abstraction: VM kernel ports, management traffic, vMotion traffic, storage traffic, and VM traffic. All these traffics are explicitly defined and separated by the hypervisor. Each VM kernel port has a semantic role, and ESXi enforces how that traffic is handled. In KVM, there is no VM kernel. Everything is Linux networking. That means traffic isn't separated by hypervisor-defined roles. It's separated by network design. Management, VM, storage, and lib migration traffic are split using Linux interfaces, bridges, VLANs, and routing. There is nothing inherently special about VM traffic. It's just packets flowing through the Linux network stack. This gives you enormous flexibility, but also removes guardrails. This slide is about the foundational networking model, not higher-level SDN platforms like NSX. Distributed Resource Scheduler is often assumed to be a hypervisor feature. It's not. DRS is a vCenter feature, not an ESXi feature. In KVM, CPU scheduling is strictly local. It is handled by the Linux kernel on each host. KVM has no native cluster-wide scheduler. Automatic placement, rebalancing, and VM relocation only exists when a higher-level product implements them. For example, platforms like HP VM Essentials Overt or Proxmox add cluster-aware orchestration on top of KVM. Again, primitives versus product features. Storage vMotion works so well in VMware because it's deeply integrated. In KVM, disk migration depends entirely on the storage backend. Some backends support live block migration. Some don't. Ceph handles this elegantly. File-based storage requires more care. There is no universal storage vMotion equivalent. Host profiles are about drift detection and enforcement. In the KVM world, this moves completely outside the hypervisor. Configuration management becomes a source of truth. Ansible immutable hosts, golden images. This replaces host profiles. Policy shifts from the platform to automation. NUMA. A quick clarification before we go further. NUMA is not about individual cores. A CPU socket contains many cores, and all those cores share the same local memory. NUMA boundaries exist between sockets. When a core accesses memory attached to its own socket, it's fast. When it accesses memory attached to another socket, it's slower. At its core, NUMA is still about CPU time allocation, which is a job of the operating system scheduler. On a single processor system, all processes compete for time on one CPU. On a multi-core system, they compete for available cores. On a multi-socket system, that competition still exists, but now we add an important optimization factor: memory locality. Each CPU socket, together with its local memory, forms a NUMA node, and performance is better when a process runs on cores within the same NUMA node as the memory it uses. On non-virtualized bare metal systems, the NUMA optimization is handled directly by the operating system. The scheduler and the memory allocator work together to keep threads running close to the memory they use, using NUMA-aware scheduling and locality-based memory allocation policies. With virtualization, an additional layer is introduced between the workload and the hardware. In VMware, NUMA optimization becomes a two-step process. First, at VM Power On, the hypervisor creates a virtual NUMA vNUMA topology based on the VM CPU configuration and the host's physical NUMA layout. Second, the guest operating system detects and uses this vNUMA topology to make its own scheduling and memory allocation decisions. Effective NUMA optimization, therefore, depends both on the vNUMA topology provided by the hypervisor and on how well the guest OS and its workloads take advantage of that topology. Now that we understand what NUMA is, let's look at how VMware and KVM deal with it differently. In VMware, NUMA optimization is largely automatic. When you power on a virtual machine, ESXi creates a virtual NUMA topology based on the VM's CPU configuration and the physical NUMA layout of the host. That virtual NUMA topology, vNUMA, is then presented to the guest operating system, which uses it to schedule threads and allocate memory. Most of the NUMA policy is applied for you, and in many cases, things just work without additional tuning. In KVM, the approach is different. KVM exposes NUMA explicitly through Linux. The VM is scheduled like a normal process, and memory is allocated using the kernel's NUMA-aware mechanisms. Unless you configure it explicitly, NUMA behavior in KVM is best effort. If you care about strict locality, you can pin vCPUs to specific cores, bind memory to specific NUMA nodes, and even define a virtual NUMA topology for the guest. So the difference isn't what's possible. Both platforms support NUMA, but where the responsibility lives. VMware encodes NUMA best practices into the platform. KVM exposes the mechanisms and lets you decide how far you want to go. vSphere HA is extremely opinionated. It includes admission control, slot calculations, and strict guarantees. KVM does not include a built-in equivalent. HA is implemented through clustering software or platform logic. Restarting a VM is not the same as availability. You must design HA intentionally. VMware FT is unique. There is no true equivalent in KVM. Closest alternatives involve application-level replication. This is a deliberate design trade-off. FT is a product feature, not a virtualization primitive. In VMware ESXi, a virtual machine is implemented as a cartel, which is a group of worlds, VMware's internal schedulable execution context, similar to lightweight processes or threads. One of these worlds is a VMX world, which acts as a VM's control plane, coordinating configuration, devices, and management, while other worlds execute the VM's vCPUs and I/O work. In KVM, the same roles exist but are built from standard Linux components. A virtual machine is represented by a single QEMU process acting as a control plane, with each vCPU implemented as a Linux thread scheduled by the kernel. When those threads execute guest code, they enter the KVM kernel module through /dev/kvm and return to user space on VM exits. In VMware, content libraries are a vCenter feature. They give you a single standardized way to manage templates and images across the entire platform. In the KVM world, there is no equivalent built into the hypervisor. A VM image is just a disk, a file, or a block device. Image catalogs and repositories exist only when a management platform implements them, such as OpenStack, Overt Proxmox, or HP VM Essentials. So the functionality exists, but it lives at a different layer. VMware standardizes in the platform. KVM leaves at the products built on top. Let's zoom in on one specific piece of that workflow, EVC. In vSphere, EVC is a cluster-wide CPU compatibility policy managed by vCenter. When you enable EVC, you select a baseline CPU generation, and vCenter ensures that every VM in the cluster sees only that baseline. Even if some hosts are newer, this masking happens before the VM ever boots. From the guest point of view, the CPU never changes. That's why vMotion feels safe and predictable. CPU compatibility is enforced globally ahead of time. In the KVM world, there is no equivalent cluster-wide mechanism. CPU compatibility is defined explicitly per VM using CPU models and feature flags, or not defined at all. If you choose host pass-through, you get maximum performance, but you're also accepting that live migration will only work to compatible CPUs. So, EVC isn't about migration itself. It's about defining a stable CPU contract. VMware enforces that contract at the platform level. In KVM, defining that contract is your responsibility. If you remember only one thing from this video, remember this. VMware integrates features into the platform. KVM exposes primitives and expects design. Nothing is missing. Nothing is worse. It's just a different philosophy. In the next video, we'll tackle networking, where most VMware engineers struggle the most with KVM. If this helped you build a clearer mental model, subscribe. This series goes deep.